Hello coders, welcome back to my channel. So in the last video we studied about how the socket system call works and how kernel is sending the file descriptor to the user space, and now we are using that file descriptor which is returned from the socket API as a server. So here we are using a bind system call to make that socket FD, whichever is returned from the socket API, and making it usable as a server. So till now we studied about socket, which only creates a kernel object. That's it. Okay. Now the bind, what it does is it will allocate the IP and the port number to our server. Using this bind system call, we are creating a server actually, right? So let's dig deep into this bind system call, which makes our socket program a server. So there is a difference between a server and a client. When we are using this socket API in the form of a server, we are using this bind system call. And if we are using as a client, we don't need to use a bind system mostly, right? So what are the inputs of this bind system call? So here we have bind as a name of the system call which we are using. We have input the socket FD, whichever is returned from the socket system call. So till now we have the kernel object, and now we are going to bind that kernel object to an IP and the port, so that it will you know transmit through that file descriptor, so that when we send some data from one system to another, it will be catched by the second system and vice versa. Okay. So here we have this socket FD, and then we have this stock adder structure. What it does is it will collect the IP and the port from the user space, and it locks that into a chunk of data and send it to the kernel and ask him, okay, you reserve this space for this IP and this port and this protocol to this bind socket. Okay, so server is not reachable until we bind success. Okay, so this is the first important thing about this bind system call. Bind assign the local IP on port to a socket to make it usable, so that the packets will flow through it, because without IP it's not possible to flow a packet from a remote system. Okay, so there is no packet yet when we are using this bind system call, because for that we need other APIs which we'll discuss in the next topics, for example listen, accepts, and all that. Okay, so for now we are taking this kernel object and we are binding to that socket with the IP and a port. Simple as that. So attach a socket to IP and port and register it to kernel bind hash for future packet routing. So simple as that. So in socket system call, what we did was we created two structures, that is stuck socket and stuck sock, that is this one. So these two structures are been created using a socket system call, and that is, you know definition of these structures are present in this location in the kernel source directory, and we are using sock alloc to allocate that structure. Okay, so this is the main structure of a socket. What we have in this, we have the state of the socket, then we have the type, we have the flags, we have some file linked with this, and we have a socket pointer to this, and we have a protocol operation, whether we are using TCP, UDP, and others. We are mapping our you know structure pointer to this to make it complete structure. So now we have this struct sock. It is defined in include net socket.h in the kernel source tree, and here is the structure. I just pasted it. So it have two things. First is the port and the IP, and the interface index if we have. So there are other things as well. You can go to this file in the kernel source tree It is been allocated when we call the socket API using skallocate. Okay, so this is update during bind. So these things, this is the XK pointer for that sock structure, and we are giving the port and the IP. I will tell you the whole program how to bind properly. But for now, just make you understand that this structure is already there by using socket system can, and we are filling this port and IP to make it usable. Okay. So after this, the system knows, okay, I am going to create a server, socket server. Okay. So this is the flow path from user to kernel for this bind system call. Okay, so first of all, we have a user space API bind. Okay, it goes to the glibc wrapper. Okay, so this libc directory is always there. That library is already there in the Linux system, so we can use that APIs. We can call through the system call, handlers and all that. So we have the system call instructions like this for bind in our glibc as well. Okay, we have a kernel entry point like this entry sys call 64, that is in the kernel when we are going to enter. But if you see here, till now we are in the user space till here. Okay, but now we are going into the kernel space. So this is all I'm telling you about the kernel space. So the first entry of this system call goes into the x64 sys bind that is defined in netsocket.c. Okay, so next we have sysbind that is also defined in socket.c, and then we are passing some fd. So this lookup should be there. Then we have this bind system operation that is being mapped, and what you say, like all the ports and the IPs been mapped here. Then we have inet bind if you are choosing IPv4, TCP, or UDP. So depending on that, we are choosing this thing. But here we are only choosing IPv4. So it will take inet bind because we already chosen this in the socket system call. So it will directly go to net IPv4 AF underscore inet for IPv4. And here we have inet connection system checker and get port. So it is defined in net IPv4 inet connection sock dot c. Okay. So after all this, we have a kernel hash table that is defined in this header file, and there all our data that is related to the bind system called got saved here. So there is this is a kernel entry for the IPN port for a particular socket to reserve in that area. We are updating the state of the stuck sock and we return to the user. Okay, so we already know we have copy from user and copy to user. So after this system call, we are giving output as 0. Like the bind system call returns 0. Okay, so for success. So we need to check whether that 0 comes so that we get to know, okay, this bind is successful. And now we go to the next step. Okay, so these are the few APIs that we are using while configuring this bind system call. So one is we are passing a sock header in to this system call as a second parameter. So the second parameter, what we did, we have a port header and add this sin family. So these three we will fill and we will pass this structure to the bind system call so that it will register this IPN port. Okay. For example, if we have this entry here, so this is the second parameter which we have sock adder uh, that we are passing by filling that structure. Okay, I'll get to know in the when we go to the code, and here we have sock operations, inet stream operations. So this structure we are passing to this ops so that this TCP related APIs is being mapped. Okay, so next is structure inet bind bucket. So this is related to this hash table that is being implemented. So it will reserve to store the ports and the list of socket bound to it. So this hash table is responsible for all the kernel related stuff for internal operation of the socket, because whenever the socket comes into the kernel, it will be traversing through these socket descriptors to go to that particular application. So this way, all of the things are working in our system, and we are able to communicate to the other PCs through this socket system call. Okay. And if you want to get a full trace of the APIs from the bind system call to the kernel space, we can use this list of commands and enable the live tracing on the Linux system, get all the APIs in flow. So here is a simple program. We already run this socket in the last section, and here we are getting socket created and get PID and all the stuffs. Okay. So after this, we have this bind system call now. So bind system call needs the file descriptor, and this is being added from here after this socket system call. And now we need to pass the structure sock header to this second parameter, and we have to pass the size of the header. So here the structure we are filling with the sin family, that will be IPv4. So we are binding to a socket with IPv4 traffic, and the port number is 8080. Okay, and here we are taking the default address in the thing, and when we able to bind this, it will give you 0 in return. Okay, simple as that. So this is the user space structure that we are filling, and we are passing to this so that it will flow through the user space to the kernel space till this hash is created. And kernel get to know all the ports and the list of sockets attached to this with this operations. If we have UDP operation, maybe we will change this operation structure, will give a secondary address to this sock structure. So the main operation is done by this sock only. Okay. And here, if I will do here, I'll take a sleep here. So sleep maybe 100, and I close it, and I gcc -o bind API. Okay, and here we have bind API.c. So if I compile it, I got this binary. Okay, and now binary this way. I'll run in background. You see here, you get a process. Okay, socket is created with FD3, PID is there, and we have the bind status as 0. It means the system is been bind now, and we got a process as well, and it's running. So if I grep -I bind. Okay, so this process is already running. Netstat -lp grep. I'll check the port number 8080. So I think there is no process till now, and our process ps-ax grep mm, find, it's in a sleeping process. So still till now we are not able to find our socket in the command. Okay, so our socket should be in the listening state or any other state, establishment state, and there are a lot of other states for that socket to be in netstat. Okay, so what I will do now, we'll go back to our program now. I think from this video, you will understand the basics, what all structures are initialized, what all things are being passed to the next API when we are using a server or a client. But the main thing of using this bind system call is a IP and a port. Okay. So the question here is, can we have the same IP and the same port for sockets or more? The answer is no. If we are using for some different apps, we should not use it. Maybe there is a conflict. Okay, so you can change either the protocol type, that same family, or the port number or the IP address. Okay, so there is one way you can reuse this IP and port same for two different sockets. The thing is, we can use a API in which we will reuse this port number, so that there is no conflict in re-registering this bind system call. Because if you see, there will be a lot of programs where you will be getting bind fail. Okay, so for that things you should be prepared. Okay, we can reuse our port to resolve that problem. Okay, that I'll also discuss. Okay, so this is all about the flow of the bind system call. If you have any query, just post a comment. I'll be more than happy to solve that. So see you in the next video. Thanks.